In this video, we will discuss how shear force and bending moments diagrams are obtained for beams. Beams are important structural members. They are long and slender, and shear forces and bending moments will be acting along a beam, and at different positions you will have different variations of shear force and bending moments. For us, it's important to find the critical sections, and for these sections, for example, in this section the moment is maximum. For this section we will do our strength of materials calculations. Well, first discuss the sign convention. If you have a beam, if you have a distributed load and its positive direction is facing to the beam, the shear forces in a section which cause a clockwise rotation of the section is positive, and the moments which cause a negative in the upper and positive in the lower part of the beam will have a positive sign. So let's start discussing the diagrams by taking a very simple beam. We have supports A and C, and in point B I have a load P. When I do calculate the support forces, it's obvious that they are P over 2 and P over 2, and let's draw the moment and shear force diagram. You see we have two regions, region 1 and region 2. Well, in order to find the internal force and moment mathematically, what we do is in region 1, for example, we do a cut at a distance x, as you see in this drawing, and we put our positive moment and positive shear forces, and taking this as the free body diagram and writing the equilibriums, then for sigma Fy equals 0, V equals P over 2, and if you take the moment for point A and write it 0, then you find that M is a function of X, and it's P over 2 times X. So for a location X, we have found the shear force and the moment diagrams. Shear force is constant, P over 2, and M is a function of X, and it looks like this. Next, we take the region 2, make a cut. This time, well, the cut is on the right side of the force P, and do the same. Sigma Fy equals to 0, sigma M equals to 0. We don't have to spend time for the details. You write these equations and you find V minus P over 2, and the moment equation gives you M equals to P over 2 times L minus X. Draw these diagrams, and you see you obtain your shear force and your bending moment diagrams. It shows that V is maximum P over 2 and M is maximum PL over 4. So you can find the maximum value when you find in these equations, for example, if you put x equals to L over 2, then max equals to PL over 4. That is this result. Okay, another example. Draw the shear force and moment diagrams. This time we have a distributed load. We find the support forces, and then we do our cuts. This time we have only one region, so well, we cut at the distance x, and you see we have here the distributed force W, and this force can be calculated as W times x. Well, the distance is x over 2. We put a single force again. What we do is the same. Sigma Fy equals to 0. And if you take this free body and write the equation and take V out, then this is your equation. And in this case, you have V times L over 2 minus x. For x equal to 0, when you put a 0 here, this is VL over 2. When you put L, it is minus VL over 2. And for x L over 2, x equal L over 2, you have 0. This is your shear force diagram. Next, for the moment, well, take a moment, again, equal to 0. Well, we take a moment around this point, and you write down the M equation. Now we have a parabolic curve. Well, you see it looks like this. And when you put for x equal L over 2, you find the maximum value. Again, we have our diagrams, the shear force and the moment diagram. The maximums are here and here. We know their locations and their values. Well, this is a method where we do cutting and make mathematical calculations in order to find the dependence of V on X and the dependence of M on X. But for this, we can use also much simpler graphical methods for constructing shear and moment diagrams. We will not go into detail, but we can say that the relationships dV over dx, that is the slope of the V curve, that is the slope of the shear force curve, is minus W. What does it mean? If you take a point here and go up, and you find that the W at this point is, let's call W1. It is a plus, so the slope at point C is minus W. For example, well, here, what is your V value? V equal to 0. That is, the slope of the V curve is 0. Where is the slope of the V curve maximum? You see over here. Well, here we have a VB. This is the maximum, and the slope in this point is minus VB. So what does it help me? So how can I use this information? Well, it's very obvious. So when you have, let's say, the support forces, in this case, when you know this value as VB and this value as VA and VB, you can put these values. You know this point, you know this point, you know the slope over here, you know the slope over here, and you know that, well, it will go down and it will look something like this. Okay, another important equation is that dm over dx is V. What does it mean? the slope of the moment curve is equal to the value of the shear force. Okay, let's take the same point. Which point? We take the point C. In this point, VC is a positive value, and in this point, the slope of the curve is positive. Well, let's take point D. In point D, V equals to 0. What does it mean? The slope of the moment diagram is 0, and here VB is negative, so the slope of the moment diagram is negative. So we will use these in constructing our diagrams. Another important info is that when you have point C and you move to point D, well, you will have a change in W, and so your V value and your D value will also change. You will have a delta V. That is the change in the shear. What does this equation tell me? It tells me that this is the area under the distributed force curve. So the change in V, the change in shear force is negative of this area. You calculate this area and put a negative sign and you find delta V. Well, similar to that, delta M. Well, you again move from point C to point D, and you will have a change in the moment delta M. This delta M corresponds to this area. You calculate this area, and it has no negative sign this time. So the change in the moment is the area under the shear diagram. The change in shear is the area under the distributed loading minus. Okay. Next, when you have not distribution of loads, but we have a single force or a single moment, so this will have changes in my diagrams as a jump. And so that will also help me to draw these diagrams. Okay, let's take this problem. Remember that we already have calculated the shear forces by cutting the shear forces and the moments for this example. So let's try to draw it with the help of our graphical method. The first thing is, well, if this is W, these are my, let's say, support forces. Next, we try to draw the shear diagram. Well, imagine that we have an empty space, empty page, and try to draw it. So on the left side, I have WL2 as a support force, okay, in this point. And is it positive or negative? It tries to make a rotation clockwise, so it's positive. Next, I have done this. And what about this? Well, it is trying to make a rotation anti-clockwise. It's negative, so minus WL over 2, WL over 2. What is the slope at this point? At this point, we know that dV over dx is minus W. So here I have a positive W, so my slope is negative. Well, the slope along the beam is constant, and you can show it like this, and this is now your shear force diagram. I didn't do any calculation, just the support forces. So it looks like that. And now the moment. We have here a pin, here again a pin. So free to rotate, so the moments are 0 over there. So what about the slopes? The slope at this point in point A is the value of V. It's a positive value. The slope in this point B is negative. It's a negative value. The slope in the middle is V equals to 0. It is 0. And so my curve looks like this. Okay. And what about this maximum force? Well, we have learned that it's equal to the area. And this area is a triangle, so you can calculate it 1 over 2 WL over 2 times L over 2, and it's WL square over 8. So this maximum is WL square over 8, and it is exactly the same what we have found with our mathematical calculations, what we have found by cutting and writing the VFX diagram and moment FX diagram. In this case, using the graphical method for drawing the diagrams, so it is much easier. Another problem. Draw the shear force and moment diagrams. Well, in this case, I have a fixed support. This is a free end. So I have to calculate the support forces. I write down the equilibrium diagrams. Well, and I find that my shear force is W0L and my moment is W0L square over 2. So let's draw the diagrams. Well, this is what we do. This is my shear force. What about the shear force? It is positive. The slope is minus. At this end, at the free end, the shear force and the moment is always 0. So I have a constant slope, which is minus W, and this value is W square L. Okay. What about the moment diagram? Well, at this end, I have a moment WL square over 2. It is creating positive on the upper, negative on the lower side. So that means it's a negative value. So here we have minus W0L square over 2. And we also know that at free ends, moment is 0. And let's draw the curve. Well, on the right side, V equals to 0. That means at this point, the slope is 0. And over here, I have a positive W0L, so I have a positive value, so I have to draw the diagram like this. So we have our shear force and moment diagrams. It was easy. The maximums are easy to find. Another problem. This time, well, we have not a constant distribution. So let's see what we can do. First, well, I write the moment diagrams. I put a force in here and I take a moment and here again. So I find the support forces. Now, having the support forces, at this end, I have a support force which tries to rotate clockwise, here anti-clockwise. That means here I have minus 3, here I have plus 1.5. Well, what about the slope of the shear force? It is minus W. So left point is, well, W equals to 0. The slope equals to 0. And on the right side, I have positive 2. So that means the slope is minus 2 kilonewton per meter. So it should start here, go here, so it's something like this. Okay, but this point, I don't know yet. Next, what about the moment? We know when you have pins free to rotate, the moments is 0, and that means the slope over here is positive. The slope is over here is -3, and the slope over here is 0, so it's not too complicated to construct the diagrams. But we have constructed the diagram, but we don't know the location, this 2.6, and in order to find this maximum, I have to calculate again this area. That will be a little bit complicated. For this, well, we need to use our cutting and shearing again. So that means graphical methods, drawing the shear force and moment diagrams, will help you a lot. But in some problems, like this, you have to do extra calculation in order to find, for example, this 2.6. What we do is cut here. Here we have a distribution. And for this distribution and for this equilibrium, I write sigma Fy equals to 0. And here I can find my V. And when I put V equals to 0, that is this equation, I find the location of the point where the shear force is 0. So this will give you 2.6. So we cannot just neglect the cutting in such cases. We will use the both methods together. In order to find the value of the maximum moment at this location, I have to use again the cut section, and here this M, I write down the equilibrium, and instead of X I put the 2.6 values, and I find as the M max value 2.6 kilonewton meter. Well, both values are 2.6 just by chance. Okay, so the last problem we're going to solve is a shear force and moment diagram where we do not have a uniform force distribution. We have, in this case, we have only single loads. Well, again, I take a moment here, find this force. I take a moment around D, I found A, and that is 4.8. This one is 11.2. Well, you know how to do it, so we'll not discuss it. So let's draw the V diagram. Over here, a force trying to rotate clockwise, positive 4.8. And this one tries to rotate anti-clockwise, so that is negative 11.2. So I start with this point. Well, in this region, what is your distributed force? It is 0. What does it mean? Your dV over dx, that's the slope of the shear curve, is 0. And so we have a 0 slope curve. That means our shear force is constant. Now I'm here. Now I have a single force. I have a jump down by 8 kilonewtons, and that will give you minus 3.2. And in this region, again, no distributed force constant. And here again, I have a jump of 8. When I jump down by 8, then I end up with 11.2 constant. So you see, I end up with the same force value. Well, that shows you also that your graphical construction is correct. Okay, this is our construction, and now we come to the to the moment, and here again pin and pin, pin and pin, they are 0, and here I have positive 4.8, here I have a slope negative 11.2, and my slope all over region 1 is W 4.8. So that means this slope remains constant along this line. So I have a constant slope up to this point. Very nice. And then suddenly the slope becomes minus 3.2. So I have to go down. And then after this point, the slope changes again. Now it becomes steeper, 11.2. I go down by 11.2, and that is my curve. And now you see I have the V curve, I have the M curve. Well, this is just clear and neat to see. And my maximums are shear 11.2. And what about this maximum force, maximum moment? Well, we have learned that. Well, when you go from point A to point B, the change in delta M, the change in the moment, is the area under the shear force curve. So what is this area? 4.8 times, well, this distance is 6. If you calculate this, it gives you 28.8. So what you do is just calculate this area and then find the result. Okay, that was a nice example, and it was our last example. In this video, we have discussed the shear force and moment diagrams in beams, how to construct these diagrams with the help of cutting and making equilibrium diagrams and finding the functions of shear and moment as a function of x location. We have learned the second method, which is a graphical construction. There we use that the slope of the moment curve is the value of the shear force. The slope of the shear force curve is the negative value of the distributed force. We have seen on our example that this will help you a lot in constructing the diagrams, and calculating the areas will give you also the changes in the values in these diagrams. But we have also seen that in some cases we need to cut and making these calculations and finding the functions, and for us it's obvious to work with both methods, with graphical and by cutting methods. Thank you for listening.